Oh, I need to actually. So I hope I have sound. And yeah, it looks like it's one of the recommended problems. So as we learn in class, um, if you have a section without vertical symmetry, and if you load it through the centroid of this shape would probably be like inside here. But if you do load it through the centroid, it adds to the bending, it adds twisting, torsion. And you don't want the torsion because that loads the the material unnecessarily. So this is a shape for which we have, it's parametric, and it tells us where to apply the vertical load to provide or to induce only bending without any torsion. So you'd have to fabricate a bracket and weld it here. And where the force go. And we need to report for this problem what this distance is. So it will be our E. I put a star. If you look at the this entry for non flexure center or shear center, this is page 424. If you look carefully, the geometry is given relative to a middle line, center line. So we need to, for our problem, we need to figure out what B is, what H is, and what C is. Okay, instead of going all the way up, I'm going to show C here because it's the same C. We have symmetry. Okay, so for H, what is H equal to? We have the thickness, it says typical. So T thickness is 0.12 inches. To get H, we need to subtract from our value 2 inches. We need to extract half thickness and half thickness. It is a full thickness. So that's going to be 1.88. 1.88 inches. For C, we need to subtract. I say subtract? Actually, I need to add. So we have this equal 5.5 inches. I need to add half thickness. So this is going to be 0.56 inches. All right, thickness is 0.12. Half thickness would be 0.06. And then we have the B value. And to get B, we need to subtract from, so B is going to be 2 inches minus half thickness here, full thickness. So it'll be 1.88 inches. Okay, so 0.56, yeah, 188. Okay, so with this, we can evaluate the ratio C over H. So C over H is going to be 0.56 over 1.88, and this comes out to be 56 over 188. This is 0.29787. Easily 0.3, shy left of 0.3, okay? And then we need to evaluate B over H. So B over H, we have B 1.88 and H is 1.88. So this is 1. So we'll be on this curve and on this line. Okay, so I'm trying to get it the best I could. And I'll read there. Was that equal to you? So I have, so 1 unit is this. It could very well be 0.45. Is that right? So 0.45, we have E over H. 0.45. We can calculate E. So it's going to be H 1.88 inches times 0.45. And this is 0.846 inches. So I have E. E measured as shown. I need to specify E star. So it means that E star, looking at the figure, is going to be the chart's E minus half thickness. So our eccentricity is going to be 0.846 minus half thickness, that is 0.06. So minus 0.06 equals, and this is 0.786 inches. Question is, do we round to a preferred size? Maybe. I mean, there are some uncertainties in using these charts anyway. Okay, so this is the load, W or F. F, we're used to using F. Was it clear? So understanding of the charts is the key to solving this kind of problems. For L-shaped channel and the split thin wall tubing, we have equations. For the lipped channel, the second last entry in table in figure 727 will likewise have parametric charts. Okay, questions here?
So you figured out the E over H using B over H?
Yes, I use this chart. Had to calculate this value, figure out this other ratio, and then you just look at what is required and what is given. Again, this is measured from the like a middle line. Okay, so if you take photographs, now is the time, and I'm going to move to a new problem. Do you? Okay. You can exchange photographs. Yeah, the charts are on page 424. So this is page 424. Okay. Let's go to another problem. A little bit different, or it will be parametric, you'll see, where we need to evaluate the stress concentration factor. So problem is 789. So there you have, or we have a, where is it? This one? Yes. I could home, select all, crop. And I'm going to move these down. View 100. And I have some blank space. Okay. So this is a cantilever with a generous fillet radius. This is where the concern about stress is. And you have unknown lengths. We need to find this out. 4-inch inside diameter pipe, Schedule 40 pipe. For pipes, the inside diameter is the main concern because they are meant to transfer fluid. And it's assembled with a 3.5-inch pipe. And there's a weldment, and it says the radius 1/4 inch. It's loaded as shown. And we want to limit, this is a stress concentrator. We want to limit the stress at location C to 20,000 PSI. What is the maximum L that we can go with? So or yeah, it's what is required. So we're having a cantilever, and there is a reaction A, and we can tell right away. So the reaction at D is going to be these two forces combined. So 700 pounds. And then there's a moment. There's a moment. The pipe wants to, or the assembly cantilever wants to go this way. I need to apply a moment that goes this way, counterclockwise, M. What is M equal to? So how do we get M? We have point D here. Yeah, you sum moments. Sum moments. So summing moments about point D have equilibrium will give us M. So we have, and I assume positive to be counterclockwise, I have M, and then I have positive negative 350 times 6, negative 350 times 8. Okay, so from here I get M of will be 350 times 14. That's 4,900 pound-foot. 4,500. It's what I have. It doesn't hurt to calculate again. So 350, I said, times 6 plus 8 is 14. So 4,900, yes. So 4,900 poundage. How's the, I'm going to erase this. How this translate into, could have stayed actually, into our diagram. So we have, the beam is half a Fran, but we need shear first. So we have for V, and it's in pounds, we start with 700, and then nothing happens up to point B, and I have drop by half of 700, and then I have a drop to 0 at the end of the pipe. Okay. And then I have the moment diagram in pound-foot, and the moment diagram will be all below the axis. So it starts with the, remember, a counterclockwise moment drops the diagram. So we begin with a drop of 4,900 pound-inch. And it increases by a slope of 500 up to point B. And then that slope goes to half and 0. So do I need a more? And then this way. Okay, there's a knee there. And we're interested in the moment at L, M at L equals. Right? So how do I get a moment at L? Will be, I don't have a value, but it will be parametric. It's going to be this area. It's going to be L times maximum moment, which is at the support. So it is going to be L times, or I can put the multiplier first, 4900 times L. Okay. How big is this one? I mean, really, if you want to show it on the diagram, this is a clear value. So it'll be 6 times 350. And this is 2,100, like, and the negative value. Okay. It should go to 0, so I should get the same if I take 350 and multiply by 2. Am I saying the right thing? So 7, and this is 6, and what? 700 times 6 equals no, this is, okay, moment here is the area under the shear. 700 times 6 feet. So 700 times 6 equals -4 to, well, I need to subtract this. That was the mistake. So this is going to be the change in moment. So it's going to be -4900. And then I have plus the positive area. So that's 700 times 6. Okay. So now I'm good. So 4900 negative plus 700 times 6 equals, that's -700 pound-inch. The moment at L, I was about to do a mistake, so the moment at L will be likewise. I have -4,900, and to it I'm adding 700 times L. So that's correct. I'm glad I verified from going from right to left. So this is going to be, well, what it is. 700 times L minus 4900. And these are pound-foot. To get pound-inch, we need to, of course, multiply by 12. Okay, so that was one. We need to state the problem requirement. So design stress sigma d has to be at the limit case has to be 20,000 psi, and this is going to be stress concentration factor times sigma nominal. Okay. And what is going to be the sigma nominal? So it's KT, stress concentration factor. We're going to figure it out. Do not forget, this is not solid. So you don't use this nominal here, okay? Because that's for a solid bar. Stress concentrator act the same even if it's hollow. Or the KT will be the same even if it's hollow. So this is going to be M at L divided by, and I have here pi properties. I can use, oh, by the way, this is a typo. This should be a 3. Okay. So I'm interested in this entry here, and I could use I and half of outer diameter. So I could use I, like I said, with C being outer diameter over 2. Or I can use section modulus. It's more convenient. It's just one number. So over S. Okay. So let's see what we can put in this equation. So I have this, and then we'll figure out KT in a moment. Moment is going to be, but we said in pound-inch. So again, KT times 700 times L, negative 4900 times 10, times rather 12, I'm sorry, over S. And S is 2.394. Again, there are two flexion formula. You can write it as sigma is MC over I or M over S, with S being I over C. And I told you what C is for this problem. We have I, yes, but we are going to use this one for convenience. You can verify that the two are the same. So if you evaluate S using this, you get the number that's listed in the table. So last that we need to do is to find what KT is. I have it as 1.8. So 1.8. How do we get it? Well, we need to evaluate R over D. So, and this is for like radius, it's given. So so R over D is 0.25 inches, and D is going to be the outer diameter of the smaller diameter pipe. So it's actually going to be this one. Okay, so over 4. And then I need to evaluate capital D over lowercase d, and that's going to be 4.5 over 4. So, am I right? So I have here for the schedule 4-inch schedule 40 pipe. The outer diameter is 4.5. Yeah, so 4.5 over, and this is 1.125. This other one is going to be, I said 0.25 over 4. This is 0.0625. Okay, I have 0.05, 6, 7, 8, 9, 10. So 625 will be here. And I need to move up until I intercept the, do we have the, of course, there's no curve, or seldomly is, 1.125 curve. I have 1.1 curve, right? And that's going to be this one. So I need to move up. And I mean, I don't know how far up will be the, I said it might be, it's in between 1.75 and 1.8. I took 1.8 conservatively. So what do you think? 1.75 or 1.8? Again, with 1.8, you were exaggerating the effect of the stress concentrate. So let's go with 1.8, like the way I've got it. And now we can solve for, so essentially you have an equation with this being 1.8. So I have this equation and solve for L. Is it good? I think you can finish it from here. Everybody's comfortable with solving the problem up to this level and then say, like mathematicians do, do you know how a mathematician drinks water from with a cup on the edge of a sink, opens the faucet, fills the cap, drinks it, put it back. Do you know how it drinks with a cup that is on the table? Takes the cup, puts it on the edge of the sink, and reduces the problem to one before. It's how they do it. All right, so this is the problem. Again, parametric, a little bit different, and it's I think it's on the list, right? 789, the recommended problems. It is on the list. Questions, by the way? Any questions here? All clear? Okay. So I'm going to erase the board and move to or I can move to the next one. Nice pictures. 1, 2, 3, and I go to the third of the problem you can solve. So let's see, where is it? Okay, it's this one. So erase the board and so this I don't think it's on the list. So it's it talks about a simply supported beam with a distributed load, which is not given, and there's a cross section or a fabricated beam out of a C channel, flanges down, and an I beam. Can you zoom in? Okay. Nope. All right, numbers everywhere. So we might have to, yeah, at some point, to rearrange this to where save on. All right, so it talks about a composite being made of two sections. And it says it's simply supported and carries a uniformly distributed load over a span of 15 feet. Compute the allowable load for the composite beam and for the shape itself. The load is static and the load is static and the American Institute of Steel Construction specification for design standards to be used. Okay, so we have the material ASTM for both. It's ASTM, where shall I put it? SY for both is going to be 36 KSI. It's part of the name of ASTM A36. So yeah, we have. Well, let's look first at the beam itself. Again, we don't know W, but we can calculate the maximum stress. So I'm drawing up a simply supported beam. And uniform load. And this is W. Okay. The span, it says, is 15 feet. And it means that reaction of the supports, we can call this L. So what's the reaction of the supports is going to be the resultant of this uniformly distributed load, which is L times W divided by 2. Okay, so L times W divided by 2, L times lowercase w divided by 2. So it should be lowercase. We usually take uppercase as weight. Units would be in pound per foot if we work this way, pound per foot. So we can share, I cannot move it up. We can draw the shear force diagram. Yeah, I'm forced to draw it here. So shear force diagram, it begins with this amount of positive jump, so L times W over 2, and then have linear variation going to negative L times W over 2. And it goes through 0 in the middle for symmetry, reasons of symmetry. So this is the shear diagram. Okay, positive here, negative here. By degrees, the slope is going to be W. And then, well, I'm forced to move the moment diagram elsewhere. It's the beam is going to be smiling, smiling. So moment is all going to be positive. And well, I can squeeze it here. We can squeeze it here, no problem. So I have the moment diagram, and it's going to be parabolic. So starts with a big slope, goes to slope 0 in the middle where the moment is maximum, and goes back to 0 with, so yeah, it's a inverted parabola, and the maximum of the parabola is going to be at the middle. How big is this moment in max? It's going to be the area of the, it starts with no moment, area of this triangle. So the area of the triangle is going to be this piece. This is L over 2. Likewise, the other one. So it's going to be half of L over 2 times L times W over 2. So it's LW over 2, 4, 8. L times W over 8. This is the maximum moment that will occur in applying flexure formula. Because we are interested in in limiting the design, design stress. So it says use AISC specifications for design stress. American Institute of Steel Construction. This could be considered a building-like structure, 15 feet with uniform load. Okay, so we state M, or the flexure formula, I'm sorry, sigma equals M over, so M, All right, we have two sigmas. So the centroid just for the I-beam is here. What's the channel? We'll move up. We need to find where the centroid is. So we're going to extract the values from the, and then do a table like on page 365 to find a centroid, to find area moment of inertia. So sigma compression is on top where the channel is. Sigma compressive is going to be this distance up. C above we used A, and then we use C below, if you remember. C below. So it's going to be C above M, that is maximum, this one M, times C above over area moment of inertia, centroidal moment of inertia for the combined section. And then, and this is a compressive stress, and then we have tensile stress below, compressive, tensile, or could have used A and B, and it's going to be the same moment max times CB over the same area moment of inertia of the entire section. Okay? So I'm looking at a channel that is rotated. So I'm going to add some information on this figure here. We know some geometry. We have this distance is 12 inches. We have the centroid for the I-beam is right here. We're going to call this shape 1, and this will be shape 2. We have this distance, which is 6 inches. We're going to call it IY. And then we have the channel now, and we have the, it's clear because of the symmetric, they don't even say, but it's right in the, the centroids overlap. There's a no-brainer to weld it to a side, right? So the centroid, this would be for C1, this is C2, and we can tell from the information in the table, we can tell this one. So I'm looking at this, and we use the notation X. Don't forget this is flipped or rotated 90 degrees to the right. So we have, and I need to move this up and then come back. So X is 0.674. What was it? 0.674 inches. This one here. What else we're going to use is going to make for A1. We need A1 and A2, the areas, and then I1 and I2. So I'm here looking at A2, 7.35 inches squared. For the channel area, it's 14.6 inches squared. And what else do we need? I said we're going to make use of for the channel. Now we're going to use IY. Okay, IY. So I need I2 will be I2 is 4.45 inches at power 4, and then for the I-beam, I'm actually going to use IX. So it's 303. So I1 is 303 inches at power 4. Okay. Then you go back. What else do we need from here? I think we have everything from this depth. Yeah, 12 inches. Flange depth, it says, was 12 inches. Okay, so we can come back with undo to this table if we need to. Otherwise, we'll turn it into some blank space. And so everything clear so far? We're going to apply flexure formula for this section and then the top section. We can also look at, it might be in the scope of the problem, what is the compressive stress here? But if we anticipate the centroid of the assembly to be further away from the bottom surface, so tensile stress here is going to be less than compressive stress on the interface between the two. Okay. Actually, this is the most stressed area. We can and it's tensile, so we can focus just on this area. But firstly, we need to find what is the centroid to evaluate these two. We don't know them, and then we need to know what is the total. I can say 1 and 2, 1 plus 2. What is the resultant area moment of inertia? Does it make sense? Okay. So we have, here's a table on page, it was 355. I should go backwards probably, it's faster. And I'm going to repeat it on the board. Come on. 365 we said. It's 65, I passed it. No, it's here. Okay, 365. What I did, I used the hard copy. So I folded the page to the left, turn it into a bookmark. So we need a table like this. Actually, I could take a screenshot and then place it in Paint. So Alt print screen, go to Paint, and then just crop, copy, undo, paste. See if we can fit the numbers in. So we have just 2 parts, nothing about the third part. And then we have area, extracted them, area 1, 14.6. 14.6, again, inches squared. And the other one is 7.35 inches squared. We're going to assume the datum. So this is the datum. So what is I1? Distance from the datum to the centroid of shape 1. It's 6 inches. I2 goes all the way here. I know this piece. So I need to, this is 12 inches. I need this distance. I need to extract from the tables what the thickness is, like right here. And I think I have it. So the thickness, we can go back, or you can go to the appendix. It's 0.387, the thickness of the flange of the channel. All right, so it means that this distance is equal to 12.387 inches. It means that the distance from the datum to the centroid is going to be 12.387 negative 6.74. And we've got it. All right, let me write it as such. So it'll be 12.387 negative 0.674. Okay, and this is equal to, I can calculate it, a calculator. All right, so 2.387 negative 0.674. 674 equals 11.713 inches. And now we can evaluate these products. Yeah, we'll evaluate the products. So 14.6 times 6, this is 87.6. It's nice to put this in a spreadsheet in Excel. And then 7.35 times 11.713 equals. This is 86.091. 86.091. These are inches at power 3. Okay. Moments of inertia. These are the centroidal moments of inertia. So it's they're going to be the 303. Again, inches at power 4. And the other one is 4.45. 4.45. All right. And now I need to get these two distances. They are the distances from the overall centroid, which I haven't calculated yet, to the centroids of the individual pieces. So we need to calculate this now. We take the sum of these two. So I overscored, measure from the datum, will be a positive value up, is going to be these two, 87.6 plus 86.091 divided by 14.6 plus 7.35. Okay, so I still have this one plus 87.6 equals over parentheses 14.6 plus 7.35 close parentheses equals. So this is 7.913 inches. I can write it here, 7.913 inches. On the figure, it's going to be CB. So CB equals, I still have it, 7.913. This other one now is going to be what? CA is going to be this piece minus this one. So I say negative plus 12.387. And this is 4.474. Okay. All right, so let's see what these D values are. So I have distance, I said, between the overall centroid and the centroid of part 1. That's going to be 7.913 minus 6. So that's 1.913. 1.913, likewise inches. And then the second one, I need to find distance from here to the centroid of just the C channel. And that's going to be the easiest. It's just to subtract from 12.387 inches the what? Actually, no. If I subtract from this value, I get this. So the distances D1 and D2 would be, this is D1, and this is going to be D2. D1, we have it, and D2, I said you subtract from 4.474, 6.74. I could even write it here. So, so the way we did it, 7.913 minus 6. So this was 1.913. And the other one, we went and subtracted from 4.474. We subtracted this piece. 0.674 was the X value in the table. Negative 674. And let's see what it is. So 0.474 minus 0.674. Okay, 3.8. Okay. And then I need to square these and multiply with area for the parallax theorem. So I still have this 3.8. I square it. And then times A2 times 7.35 equals, that's 106.134. 106.134. These are inches at power 4. And then for this other one, I take 1.913 multiply by 14.6. And this is 2793. 27, it's actually 27929893. Okay, so I need to calculate these and then add them, the last column, and that's going to be the total moment of inertia for the assembly. So I1, what was it? It's here. So 303 plus 2793. I still have, so plus 303. This is 330.929893. And then the second one, it's 106.134 times this guy, we said, times, what are the added to I2? So plus 4.45. Is there a homework due tomorrow? Still working on it? This is in line with the homework. 110.584. Okay, so I, total of the assembly, I think I used 1 plus 2. 1 plus 2 is going to be these two added. So I need to add, this is on computer screen, or calculator screen, plus 330.93. And it's 441.5 inches at power 4. Okay, so we have the area moment of inertia for the composite beam. These will be the maximum moments, and we need to evaluate or rather state, because we don't have a moment yet as a value, we don't have W, we have L. L is, we need to change it from 15 times 12 to, so it's 180 inches. This is L. Okay. So if you go at the back of the book where mechanical properties ends, it's page 790. We have design bending stresses. So general machine and structural design, and then it says B, AISC, American Institute of Steel Construction, structural steel, static loads, or building-like structure. How it appears to be a building-like structure given the span, 15 feet. Okay, so for steel, the design factor is going to be 1.5. Okay, so or 0.66, or we'll just say SY over 1.5. So design factor recommended N is 1.5. Okay, so I'm looking at these two here, and I'll say, let me state this again elsewhere, I1 plus 2 is 441.5 inches at power 4, because I need the space. Okay, so starting with compressive, I use C and T. It would be nice to use compressive on top. Let me switch to A, above and below. This will be a negative stress because it's compressive. So above, it's compressive. stress. And I have sigma above. I'm repeating that equation, or rather with L 180, 180 times W, which you want to find, over 8, was it? So this will be the design stress equals to SY over design factor 1.5. So it would be 36,000 PSI over 1.5. We solve for the first W. And then I stay the same below, which is tensile. And then I say below stress is 180 times W. Well, one thing I missed is I wrote just the moment. I apologize. So I need to go back. So this is the moment, and then it will be times C A, which is 4.474. I need to move this. I'm sorry. I went ahead of myself. So the moment, and then will be times CA, which is 4.474. This is CA over the area moment of inertia that we calculated, which is this one, 441.5. And this is going to be SY, that is 36,000 PSI over 1.5 design factor. Okay, and here likewise, so the moment times, now we have CB 7.913 inches, 7.913 inches over the same area moment of inertia, 441.5 equals, at the limit, 36,000 PSI over 1.5. You solve for the two W's and you pick which one. Is it clear? So you're trying to take notes. You'll also take pictures at some point or at the end. I'm going to find two different values, with this one being less by just looking. So I have what? I have a 7 versus a 4. Divide, everything else is the same. So this second one would be the solution of the two you report as solution, the smallest one. We can actually solve for the two. So above and below, kind of, not as above, below, from consideration of stress above, below. So, and I said the second one, it's clear that was going to be the smallest one. So how do we get it? It's going to be 8 times, so let's say 8 times 441.5 times 36 exponent 3 over 1.5 over 180 over 7.913 equals. So this is 59513.88 pound per inch. Now, if we want it in pound per foot, I divide by 12. So this will be 4959.5 pound per foot. And this is the answer. The other one will be a bigger value. I can actually calculate it. So what do I need to do? I need to divide by 7.913, multiply by this. So over 7.913 times 4.474 equals. Oops. Is that correct? So I've got the smaller value. So once again, if I have, oh, it should be the other way around. Let's calculate the standard weight. So 3/6 exponent 3, this one times 8 times 441.5 over 1.5 over 180 over 4.474. equals, yeah, so 105,260 pound per inch. And if I divide it by 12, I get 8771.67 pound per foot. Yeah, that almost double value. Could have did what I was explaining, but instead I should have multiplied by this and then divide by this, because it's flipped. Anyway, we finalized calculations. The from consideration not yielding in tension the lower part of the beam, the uniformly distributed load should be up to this value. Tempting to report it as 5,000 pound per foot, but you're at the verge. There's a flock of birds going south or coming north in spring, and the straw that broke the camel's back. All right, so this is it. Thanks for your patience. So homework due tomorrow. And yes. Yeah, if you have a university, an island ID, you should be able to access on any computer that's 214 or 316 in this building. I think there are other computers on campus that have AutoCAD.